Welcome to this Itasca featured video. In this tutorial we will demonstrate how to create a fractured synthetic rock mass specimen. Rock masses are complex systems made of a rock matrix often riddled with discontinuities, such as fractures, joints, and faults. Such systems can fail in the matrix or along discontinuities. With PFC, you can study the mechanical behavior of such systems due to the smooth joint contact model. This tutorial will guide you through a modeling approach to create a synthetic rock mass specimen that can be further tested to determine its strength characteristics. This will be done by creating a brick in periodic space, which then will be assembled into a full-scale model, creating a large-scale bonded particle model, generating and simplifying a discrete fracture network. Lastly, is the discrete fracture network used to assign smooth joint contact models to contacts that intercept the fractures. Open the tutorial by going to Help in the menu bar and choose Examples. Under PFC, Tutorials, and Fractured Rock, you find the project file Fractured Rock. The project consists out of 4 files. The file, do all, calls the other data files, one by one, which perform each step of the modeling process to lastly create a fractured rock mass model. This strategy can be useful if you want to manage multi-step simulations effectively. Start by executing the first line, which sets the model title by right-clicking and choosing Run Selection, or use the shortcut Ctrl-Shift-E. The data files, make brick and make intact, creates the intact specimen in 2 steps. Firstly, a small system is equilibrated in periodic space. Then this system is used as a brick and assembled to create a larger full-scale model. The last data file, make fractured, will superimpose fractures onto the intact bonded particle model. In the end of each data file, the command program return is called. This will return the command processing to the calling file. The first data file being called is makeBrick, which will create the brick in periodic space. This means that when a ball centroid falls outside of the model domain, they are translated back to the opposite side of the model. To ensure that contacts are created, as if the model was continuous, ghost balls are introduced. For now, the goal is to build a dense and well-connected assembly. Set the general model control by marking and executing the first 2 lines. The first line clears the model, which is useful if you will run the file multiple times. The second line sets the calculation mode to be large strain. Create and define the extent of the domain. By adding the keywords condition and periodic, you apply the periodic domain boundary conditions. The contact model assignment table consists of an ordered set of slots, along with a default slot for each contact type. This means that the contact model assignment table controls the assignment of contact models and properties to newly created contacts. Here the default slots of the contact model assignment table are filled with the linear contact model with specified normal stiffness. The balls are generated and distributed with overlaps in the entire domain extent. The process continues until the target porosity is reached. Note that the keyword resolution is used, along with a value of 0.1. which will multiply the specified radii. The attributes, that is, the characteristics, of the balls are also set, the density and local damping. In the plot system, you can see the overlapped balls within the domain. The overlaps may be reduced by letting the balls rearrange. This is done with these commands. To efficiently remove the energy from the system, the command model cycle with the keyword COM is used. The system is then solved to equilibrium. The command brick make makes a brick from the current model state. And the keyword ID sets a specified ID number to the newly created brick. The second line exports the brick with ID 1 as a binary file, as this brick will be used later. The keyword skip errors overwrites any existing file with the set name. As the current file was called by another file, the command processing returns to the calling file, do all. The second data file being called is make intact, which will assemble the brick in a full-scale model and install the linear parallel bond contact model. The first command clears the model state information, and the second command sets the new extent of the domain. Import the brick from the binary file and use a series of bricks to assemble the model. The brick is replicated twice in the horizontal directions and 4 times in the vertical direction. The keyword origin sets the position of the origin of the new assembly, for example the lowest location of the first brick used. In the plot, you can see the assembled brick to the left and the linear parallel bond model to the right. Note that the default slots of the contact model assignment table are not modified when the brick is imported. They are modified by assigning the linear parallel bond contact model with the keyword lin mode set to 1. This property sets the normal force component to be updated incrementally based on the surface gap increments, with the update type controlled by the normal force update mode. The deformability method is used to set the micro properties to meet a target Young's modulus for the linear portion of the contact model. Lastly, apply the contact model assignment table to the existing contacts. Set the ball attributes, contact forces and moments, to 0. By setting these to 0 and changing the normal force calculation to incremental mode, the built-in stresses from model construction are removed. With the command contact method, you bond all overlapping contacts between the balls. The assigned parallel bond properties are set accordingly. You would not want to enter the bond method in the contact method assignment table, as it would try to bond all the following created contacts. Save the model state as intact. Lastly, return the command processing to the calling file. In the plot, you can see the assembled brick to the left. To the right, you can see the contact model plot, showing the orientation of the parallel bonds. The last data file being called is make fractured, which will superimpose fractures onto the intact bonded particle model by generating a DFN and then installing the smooth joint contact model at contacts intercepted by the fractures. Restore the previously saved model intact. By adding the command model random with a fixed seed number, the same model will be created anytime the file is executed. Create a fracture generation template named 1. Define the distribution of fracture sizes and fracture size limits. In this case, the fractures follow a power law size distribution with the exponent -3 and length limits of 1 to 100 units. The fractures are then generated from the statistical description with fracture generate. The DFN name is specified and the fractures generated according to the specified template 1 within the rectangular generation region, which is set to size of the assembled brick. A stop criterion for the DFN generation is based on the fracture frequency, or P10, along a vertical line. The DFN is then altered with the command fracture combine. This will simplify the fractures by merging fractures that have similar orientations and are spatially close to one another. Prior to this merge procedure, the number of fractures may be unnecessarily high, so this may be desirable. Lastly, install the smooth joint contact model in contacts intersecting the fractures. The smooth joint model simulates the behavior of a planar interface with dilation, regardless of the local particle contact orientation along the interface. Note that any contact model could be used. Save the model state as fractured. Lastly, return the command processing to the calling file. In the plot, we can now see the final 3D system. To the left, the assembled bricks of particles. To the right, the discrete fracture network. By combining these two, you get the fractured synthetic rock mass specimen in the middle. The parallel bonds, shown as green, represents the rock. The smooth joint contact model, shown as red, represents the fractures as defined by the discrete fracture network. Thank you for watching this tutorial. For more information about PFC and synthetic rock masses, see the description box for more information.